Hola. Prueba, prueba. Bueno, hola. Bueno, nuestra próxima presentación va a ser sobre juegos en Android. Entonces presento a Dan Galpin, Developer Advocate en Google, y va a hablar acerca de juegos en Android.
Right. All right, me llamo Dan Galpin. Esta charla es sobre la migración juegos de C y C++ a Android, and I'm redoing the rest in English. Sorry about that. But, oh yes, very important. Animations. So about this talk, how many of you out there have developed an Android application before? All right. How many of you have developed a video game before? That's great. That's great. That'll be very helpful. I'm going to go through a bunch of topics that will be useful to game developers, even if you are not going to be developing using the native code, using the NDK, which is the primary focus of this talk. Now, let me get one more show of hands. How many people have actually done native code or NDK programming in Android before? All right, so this will be a good introduction for everyone. So you see the agenda. I'm not going to read things off the slide. Why Android games? Well, first of all, let's talk about why Android. We're an open platform, and that's really awesome, and for a lot of reasons. And my favorite reason is that I like to see how other people write code. And in Android, you can go and look and see how most of Android is actually written, and that's really useful to me. That's why I like programming for Android. But also we have open standards, like OpenGLES, which is in every Android device. And in Gingerbread and beyond, we have OpenSLES. And of course, a lot of people have Android phones. We have over 135 million phones activated. And we are activating 550,000 devices every day, which is amazing, because those are all people who are looking for what? Well, they are looking for games. As it turns out, they're the #1 installed thing on Android devices. They're looking for entertainment. In fact, in the United States, 9 out of the 10 top grossing applications, the ones that are making the most money, are games. And that's pretty amazing to me. Now, it's not true in Mexico yet, because I think people here consider it a business tool. But I think as more and more people get Android devices, we're going to see more and more demand for games. So let's talk about programming Android in C and C++. Now, I'm a huge fan of Java. And how many people out there are big fans of Java? But it turns out that people like to program in other languages other than Java. And there's a lot of code out there. So one is that we want to make sure that people can reuse code that's already there. 2, there are certain things that Java is just not very fast to do. It's not very good at decoding video streams and doing a lot of binary parsing. It's really not designed for it. And of course, we can take advantage of really cool hardware, such as vector floating point hardware and neon hardware. And finally, it turns out that people write games for other platforms other than Android. And so having C and C++ development allows people to quickly bring games over from other platforms. So why not native code? Well, first of all, if your existing code, let's say you have it on some device, takes advantage of a bunch of OS frameworks, it doesn't make sense to try to translate that into C and C++ a lot of the time. Also, the C and C++, the native tools, don't contain UI building components. So if you want your application to behave like an Android application, it's a lot harder to write it in native code. And of course, the tools and the development experience when you're programming Android in its native platform, which is Dalvik, is just much better. So if we look at it this way, on the Dalvik side, there's a lot of great things. It's extensible. It works across multiple processor architectures. It automatically takes advantage of features like hardware floating point, and it has access to the Android API. While on the C++ side, you can write tighter, faster code. Now, it doesn't necessarily happen, but you can do it. It's low level, and it's common on a lot of other platforms. So what do you get in this native development library? Well, this is the first version. So as of about a year and a half ago, this is what you got, which is pretty good. You get the ability to run most C programs. You get the ability to talk to the screen using OpenGL. When Froyo came out, we also added something called libjni graphics, which allows you to actually compose graphics using native code. It's a very powerful thing to do. A lot of people want to be able to do that. And then in Gingerbread and beyond, for tablets as well, of course, we added actually a bit of a native framework. And as of this point, you can write an entire application in C and C++ without having to write a single line of Java code. So if we think of this as being the Android architecture, and this is a slide that they don't even like me using anymore, but it kind of shows all the basic pieces here. This is what's available in the most devices running the NDK. So you do lose out on a lot of things, and in fact, this is what you get back in Gingerbread and Honeycomb. And there are only pieces of these that are available. So unless these are the only things you want to talk to, you're going to end up having to write some code in Java. So what's inside of the box of the NDK? Well, one is you get a pretty cool tool chain with a bunch of standard cross-compilers. You end up getting this really fancy build system, which is written in Make, but it's pretty much the same build system we use to build Android itself. And you get headers and libraries. And this is kind of important because you need to have a stable binary interface. So what you want to do is have this Android application, and your Android application wants to be able to talk ultimately to these system libraries. So this is the Dalvik side of things, and this is actually running in native code. So your libraries want to fit there. But if they talk straight to the system libraries, that's going to mean that they're not going to be compatible. Because ultimately what's going to happen is we're going to change the implementation underneath. So what we've done is we've created a stable binary interface that slots in here. So your code can go and talk straight, essentially, to these libraries that underlie all of the Android framework. And we've pledged to keep those compatible across versions. So I'm going to go through a little bit about how to use the NDK. The first thing we have to do is install it. Very, very simple. In fact, if you're running a Linux box, it's very trivial to do. On Windows, you're going to want to install Cygwin. We're going to try to fix that in the future, but today it is required if you want to use some of the build scripts. All of the tools are actually designed to work both within Cygwin and outside of Cygwin. And this is the basic development flow. So first of all, we set up the project. And it looks just like any other Android project. These files, build XML and some properties, are created by those scripts. But we're going to add something else. We're going to add makefiles. And these two makefiles are actually things you're going to generate that are going to explain, of course, how to build a C and C++ code. So the first one is android.make. This basically is used to build the individual source files. So you see we have what file we're including, libraries we need, very, very much in traditional make style. The secondary file is actually the application make file. And this gets a little bit more interesting because it includes something called app ABI. And what that allows you to do is actually say which hardware platforms you want to target. In this case, I'm targeting ARM 5 and ARM 7. And it's actually going to build two separate libraries. And the Android framework is going to be smart, and it's going to pick the library that's going to work on the device that we're actually running on. The other thing we need to do, of course, is write interface classes, because ultimately, what our NDK component is really just a piece of a larger Android application. That's how this fits in. So we need to be able to call it from Java code, from the native Android development environment. So what we do is we take advantage of JNI. And this is actually pretty straightforward. We write our interface class, and our interface class contains the native keyword. As you can see, I've actually got two functions here. One that's actually a member of the class, and one that's a static member of the class. And it will actually be able to automatically generate the code for that using a tool called Java-H, which is going to take those two functions, and it's going to generate this nice prototype for us for C and C++. And all we have to do ultimately is write a C++ module that fills these in. Now, what is it actually doing here? Well, you see there's our package, and there's our class, our function name, and there's our parameters. As you can see, they automatically are translated for us by the tool into this header file. Now, you can see we have a JNI environment, and this is really important. That environment is what our native code uses to talk to the Dalvik virtual machine. In addition, we have an object pointer, because as we recall, the init method is actually a member of the class. But because the other function is static, what we actually get is a reference to the class itself rather than to the object. So the other thing people want to do, in addition to being able to call native code from Java code, you're also going to be able to call into the Dalvik virtual machine from C and C++ code. And the way we do this is pretty straightforward. We simply can get the class for this object, and from this class we can use reflection to get the method ID. In this case, in this particular case, we're going to call take key events. And then we can simply call that method using the environment. And there's a lot of examples of doing this, but that's how simple it is to actually call a bit of Dalvik code from within native code. Some important things to note about this JNI thing. One is that the JNI environment is intended to be passed into the function, and when that function terminates, it goes away. The same thing is true for class and object values. Also, JNI environments can't be used across threads. So these are all things to keep in mind. That being said, the expensive parts of reflection, getting the J field ID and the method ID, can be done once. So it's important to note this. Sometimes doing these things will work on some devices some of the time. And so it's important to keep these rules in mind, because ultimately it can make your application less and less compatible. So then we build. Pretty straightforward. I have bash there just because we might be using bash in a Windows device rather than a standard shell. Then we run our standard ant debug and our standard ant install. Debugging is interesting. What actually ends up happening is on the device, we're running the application, and we run the GDB server in the process of that application. That talks to our host over a named pipe, which is important because we don't want the application to have internet permissions just so you can debug it. And then finally, it talks to Eclipse using, or whatever your host happens to be, using something called GDB-MI. And an important tip, you're definitely going to want to debug on Gingerbread or beyond, especially if you're writing games. And the reason why is that very, very few games will run in a single thread. Most games are going to want to run in a second thread that actually is processing the game loop, and a single thread that is actually talking to the UI. This keeps the game responsive and also allows it to run independent of things such as frame rate very, very easily. Unfortunately, prior to Gingerbread, debugging did not actually work very well if you had multiple threads. So this is a good reason to get a Gingerbread device if you're going to do native games. let's talk a little bit about native activity while we're here. Now, if we look at the devices that are accessing Android market, and these are as of about 2 weeks ago, this is what we're looking at, we can see that it's actually a pretty good pie chart. We're actually seeing right now about 81.5% are actually using Android 2.2, which is awesome, and 96.7 are running 2.1. But we still have only about a quarter of devices out there that are able to take advantage of native activity. So as of today, it's not something you'd want to use as your primary method of writing a game unless you're targeting only tablet devices. However, perhaps next year it will be something interesting. One thing that is interesting, though, is if you look, and this was also something that Tim talked about in the keynote, if you look at the number of downloads that users of different platforms actually make, we see that that tablet and Gingerbread users are actually downloading more applications. And that makes sense. Obviously, these are earlier adopters, and also the platform is getting more rich and more accessible to applications. I'm going to try to put the microphone a little bit closer to my face here so we don't keep losing me. All right. So you might actually want to say, use native activity in an application to optimize it for one of the newer platforms that we know people are downloading lots of games for. And we can do this using something called platform-specific resources. And this is, in general, a good thing if you are developing an Android application that you want to have 2 different versions of code that work for different platforms. So this is a general thing that's, I think, worth talking about, even beyond the scope of actually developing code using C and C++. So as you see here, I've got 2 sets of resources. One is in values, and one is in values-v9. I'm defining 2 booleans in each one at least gingerbread and one not gingerbread, which I alternate. What I can then do is go to the manifest, and I can actually enable an activity based upon those variables. And this means what's going to actually happen is it's going to launch either the native activity, if I'm running on Gingerbread, or above, or it's going to launch the old compatible activity if I'm running an older version. So this is useful in general. If you want to make an activity that takes advantage of new honeycomb features and implement it in the same kind of application, you can use the exact same technique. But it's useful in this case. The other thing that I do to make this work well is I create actually some stub libraries. And this shows off some features of the build system, which is the other reason I like to talk about it. Because not every application fits easily into one library. A lot of times people try to use more than one native library in their application. And this is how you actually create an Android makefile that can take advantage of all of it. So in the base Android.make, I simply call all of the ones that I want to be all of the other makefiles that I want to be able to include. I think I should probably switch to the handheld mic. Is that good? All right. rather than having that one keep cutting out, I'm just not going to walk around as much. So so this is how you call the individual makefiles within there. And the application.make now, we have a list of modules. So in addition to just the main module, which in this case is lib San Angeles, we also have one for native code, and we also have one for the JNI version, the compatible version. There we are. So what we actually have inside of these makefiles is something pretty straightforward. We have one that actually uses just what's available in the older Android releases, which is OpenGLES, logging, a few other things. And then finally in our native version, we actually link to all the other libraries. So it's pretty straightforward. Now, the only thing that's slightly tricky about this is that the libraries have to be loaded in order. We don't actually have dependency checking in our library loader. So what I do is I simply subclass native activity, tell it to load the primary library, San Angeles, which the other two are dependent on. And then in this case, for the regular activity, they can just be loaded in order. This is how you end up loading libraries in native code. So just a little bit on native activity, if you want to get used to it. How many of you have actually seen the Xperia Play device, the one that actually has game controls? So native activity is currently the only way to get to those touchpad inputs. So some people are interested in being able to use native activity for that reason alone. So let's talk about the key components of every game. We have graphics, input, sound, and I like putting life cycle in there as well because it's important to recognize that Android is a multitasking operating system. So, OpenGL. First of all, every Android device supports OpenGL. Now, and almost all of them support a hardware-accelerated version of it. Also, over 90% of devices now support OpenGL 2. And they're used both in 2D and 3D high-performance games. And here are some examples of some commercial engines and some open source examples that you can use to build these games. And even though we're using native code ultimately to do a lot of the manipulation, we're still going to want to use GL Surface View, which is something that sits inside of Dalvik. And the reason we're going to want to do that is because OpenGL contexts are shared between native code and Dalvik. And it also does a lot of work for us. It actually creates a rendering thread for us, and it also does a bunch of things with contexts that are useful and actually help to maintain compatibility. There's a few things we have to do when we lose our context, but the point is this is a very good helper for us. Other things to think about in graphics are how we draw. And in a lot of early Android devices, they were using very specific architectures. And as we move forward, we've got actually now 4 different common GPUs in Android devices. We have, and GPU families, I should say. We have the Mali GPU, which is used in things like the Galaxy S2. We have the PowerVR series GPUs, which are used in things like the original Droid, as well as the Nexus S. We have the Qualcomm Technologies GPUs, which are used in things like the Nexus 1, the Droid Incredible, and other devices. And then finally, we have the NVIDIA chips, which are used in things like the Motorola Zoom and the Galaxy Tab 10.1. And so the important thing about this is that on some devices, draw order is important, and on other devices, it isn't. But in general, drawing front to back and taking advantage of Z ordering is going to always be faster on almost every device. Also, using something called vertex buffer objects is important. Vertex buffer objects are supported on every single one of these chips. And so it's not even really necessary to check for it, with the exception of a few emulated devices. And then finally, as far as textures are concerned, in general, we want to use power of 2 textures, because if they even work without power of 2 size textures, they'll be very slow. It's just a little bit about drawing for performance. Finally, things to talk about in terms of screen size. As it turns out that 2 screen sizes represent most of the volume on Android. But it's pretty straightforward with a lot of games to figure out how to support multiple screens. One game that does it with tiles is Replica Island. And what it does is it actually uses a fixed height across all devices, and it relies on OpenGL to scale. And it looks pretty good on a lot of different devices. So when I think of Android, I try not to think of it in terms of all of these different screens, but I think about it in terms of these aspect ratios, and trying to make sure my game can handle those correctly. And in some cases, if your game has a fixed layout, that means just being able to have something pretty that extends around the border. In other cases, it means stretching the game. In the case of Replica Island, it meant adding additional tiles and making sure that the game design didn't suffer from being able to display a few or a few more, a few less tiles. Another thing, of course, that's important is audio. And Android actually contains 4 different audio APIs, and it's important to understand when to use them. Media player is the most straightforward. You hand it a media file, and it starts playing. Ultimately, what it's meant for are things like background music. It really doesn't work well for sound effects, but fortunately we have an API called Soundpool that works pretty well for those. Soundpool allows you to take a bunch of sound effects, load them into memory, and then trigger them when they're needed. We also have something called Audio Track. And Audio Track is only good for PCM uncompressed data, but it allows you to ultimately generate audio within the application. And a lot of native development applications actually use this. And then finally, when we get to Gingerbread, we've added OpenSLES, which allows you to actually generate audio straight from native code, combining essentially the capabilities of Media Player and Audio Track. And an example of a game that does this is actually Dungeon Defender's First Wave, which is a very high-end game, and they wanted to make sure they were being as efficient as possible about generating audio. So they use Audio Track to play mixed PCM audio in Android 2.2, but use OpenSL on things greater. Simple stuff. We also need to get input into our game. Your device most likely has capacitive buttons. What we mean are the buttons are really an extension of the touch screen. So one of the things we did in Android 2 was we actually changed things. Most buttons in Android 1.5 and above, we actually triggered everything on key down. And when you're using capacitive buttons, what you try to do is avoid accidental touches. So we want to make sure that the user actually pushed down and released the button on the same spot of the screen. So that's a positive touch. So the actual Android framework helps you with that. We also, of course, have essentially a touch gesture in terms of on-key multiple press or long key press that you can use to make sure your application continues to behave like a standard Android application. We also have touch handling, of course. Most games are going to want to make use of that. And we have different text detectors to detect gestures, which are important because, again, those gestures also behave similarly on all Android devices. And of course, multi-touch is important, and you can actually determine whether your device can support multi-touch, filter on it in Android Market, and also determine whether it can detract distinct points. Trackball handling is cool. A lot of devices have trackballs, and it's fun if the game can actually support them. Otherwise, they turn into these very slow D-pad events. And then finally, of course, motion handling. And the real key thing to note with motion handling, there's kind of two important things. One is that you want to make sure that you're not using faster motion detection than you need, and that you're not enabling it when the game isn't running. And I'll talk a little bit about that when we get into lifecycle. The other thing to note is that devices that default to portrait will orient the accelerometer differently than devices that default to landscape. So if you only check your accelerometer code on a phone, you will find that it doesn't behave properly on most tablet devices because all of the new Honeycomb tablets are currently landscape devices. Now, fortunately, there is this little bit of code here that you can put in, which actually changes the canonical orientation correctly for you, so you can kind of ignore this. And this is actually something that NVIDIA has on their website. So I like referring it to them, since they've done a nice job documenting this for us. And then finally, Android devices have more than one button. So it's very important to make proper use of them. People expect the back key to do something. The volume button should work. So you shouldn't handle the volume button keystrokes yourself, pass them to the framework, and make sure that you're setting the volume control stream. Because there's nothing worse than having a game load up. Exactly, volume control is important. Having a game load up that you know is going to blare a bunch of audio, and then realizing that you're adjusting the ringer volume while it's loading. So again, a very good thing to do. Finally, navigation keys, as cool as they are, can drive gamers crazy because they're very easy to press accidentally. So it's better to do things like give the user a chance to pause on back, and of course, save state. And Replica Island does a pretty good job of this as well, so I like bringing it up again. They actually allow you to configure whatever keys you might want to have to play the game. And this means that Replica Island, without any additional work, just managed to work with the Xperia Play, which is kind of cool. So let's talk a little bit about the activity lifecycle. I like bringing this up because if you're writing a game in native code, you actually have to be a little bit more responsible than the standard Android application. In truth, any application that uses multi-threading has to think about the life cycle. And this is the activity life cycle, which is not the same as the process life cycle. It's important to recognize that difference, because Android keeps application processes around as long as possible. So even if your activity is closed and destroyed, the process continues to run. And what that means is if your threads in that process are not properly terminated, they're going to continue to run in the background. And this makes Android users very mad because they realize their battery life has gone down since they've installed your game or since they've played your game. So it's important to actually do that. Another thing to note, especially if you're using native code, is that static initializers are very, very problematic because of the process lifecycle. Because when you reload that library, it's only going to happen once. And there's no way to unload it, and there's no way to reload it. So basically, the first time it gets loaded is it. So basically, don't assume that the static initializers are actually run in your onCreate of your application. And again, you have to be very careful with threads. Another thing to note is that the gameplay should stop during onPause, and that all threads are terminated in onDestroy, including your native threads. Let's talk just a little bit about troubleshooting. I mentioned this a little bit earlier, but JNI can be very, very problematic with threading because ultimately each context is per thread. So if you try to access the JNI context from an unrelated gain loop, this can cause all sorts of bad problems. And there was actually an application that shipped that did this, and it was just crashing randomly on different devices. And it took us quite a while to figure out why that was happening. So the thing to do is to either make two different loops like that, or to actually call it through the basically create a message, send it to one thread and call it from the other. Let's talk a little bit about asset handling, just because it's important, and people always ask me this question. So how does one read an asset out of the APK file from within native code? A lot of times you don't want to have to deal with passing that entire binary across from the Dalvik virtual machine to the native code. And it's pretty straightforward. Android supports something called an asset file descriptor. And this is actually an important concept within Android because it's ultimately how Android does things like play video or play audio out of an APK file. By default, what ends up happening is those files get stored uncompressed in the APK file, and an asset file descriptor containing an offset and length is passed to the media framework. So when you rely on this exact asset file descriptor, you're actually using the same technique that the media framework itself uses to play things. You can also use a native zip utility, which is potentially less future-proof, but faster from native code. And you can also use the native asset manager, which we added in Gingerbread for this very purpose. Just a few more tips and tricks. As far as performance is concerned, you can check for older hardware using CPU features, and you can create fallbacks for it. And one thing you can do is use 16-bit textures, because as it turns out, most of the older devices really are optimized around 16-bit textures, and newer devices, you'll get that much more fill rate. Most of the bottleneck in terms of Android games is fill rate. The other thing you can do is use a smaller render target and scale up. And there's a little used but important function inside of Surface Holder called set fixed size. So if you set that fixed size, and please do it to something that has the same aspect ratio as the screen, but you don't have to. It'll stretch it either way. What it'll actually do is when it composites the screen inside of something we call Surface Flinger, it will automatically expand your render target to fit the size of your view, which is very, very useful because it allows you to gain fill rate. And pixels are very expensive, especially on tablets. Tablets are ultimately even more fill limited than most Android devices. But if all else fails, you can rely on Android Market. You can filter by instruction set. You can filter by GL version and platform release. And then if that all fails, if that's not enough, you can also eliminate specific problematic devices. So, stand out from the crowd. Use Android backup and restore service. I can't tell you how frustrating it is for me to play through 60 levels of Angry Birds and then lose my device, and then have to play all 60 levels over again. I mean, in fact, what I do is I don't do it, and so I'll never play that game again. So backup service is cool. Exporting install to SD is easy. It's as simple as setting a manifest flag, and you should do it. Other things that are kind of cool is building a live wallpaper or a widget. Live wallpapers are kind of awesome because they actually make your application show up in a separate category within Android Market, in addition to whatever category it is in. And widgets are just cool because you get to own the user's home screen. And especially if you're writing something, a game that has an element where you're creating something or building something, that's important. Profiling is cool because it makes it run on more devices. The better your game runs on the more devices, the better it's going to do in Android Market. And then finally, everyone should take advantage of analytics. And I think I even mentioned it again here. Analytics is important because it allows you to know your customers. So use them. You can actually find out what drove the user to install your title by using market analytics. And you can also find out things like where people are dying inside of your game, or who it is, where the users are located who are playing your game, which will allow you to target things. So social and-app payments are really important. I think you heard Tim mention that in the keynote. Here's some development tools. I'm just going to put these up for a minute here so you can snap them. These are really, really useful. The debug manager for Eclipse allows you to integrate Eclipse automatically with the debugger. WinGDB, if you want to use Visual Studio to debug native code, you can actually do that. There's also a way to use Microsoft Visual Studio to actually build the Android NDK stuff. There are performance tools. All the major graphics vendors actually have an Android performance tool that allows you to figure out what's happening in your drawing. And then finally, consider helping us out. All Android tools are developed completely in the open, and we're always accepting contributions, and we have a list of things that we want to have done. So now we have just a few minutes for Q&A. So I guess I put this